Bismillahirrahmanirrahim. Assalamu alaikum. This is our lecture number 23 of Advanced Electromagnetic Field and Wave. And in this lecture, we are doing chapter number 10 of Jackson, which is scattering and diffraction. And in this lecture, we are going to discuss about the scattering by a small dielectric sphere. So, what is basically scattering by a small dielectric sphere? We already defined our diffractional scattering cross section in our previous lecture. If you forgot, first watch that video, then move on towards this video. This is one of the application of scattering, how by a small dielectric sphere. So in this, basically your incident field has to become inside your contact with the dipole which has positive and negative uh, charge or ions inside. So what positive ions move towards the negative ions. Okay, so in dielectric sphere, the important thing is that there is no magnetic response, there is only electric response. As there is no magnetic response, so our this magnetic response expression got 0, and we will only left with this expression till here. Okay, so as first very simple example of dipole scattering, we consider a small dielectric sphere, okay, of radius a. So if there is no magnetic response, so your mu r basically equals to 1. So only mu basically equals to mu naught, and mu r is 1, so only mu naught. And your electric, because there is electric response, so that's why E equals to E naught and E R. Okay, and because there is electric response, so the electric dipole is this, which can be written as Px xt, which is equals to Px and e power minus iota omega t. In this, basically, the electric dipole moment can be written as this expression: P is equals to 4 pi epsilon naught ER minus 1 divided by ER plus 2. Okay, and A cube and E incident. Okay, so this is how you can write your electric dipole in term of dielectric sphere. Whereas you know that E incident basically equals to epsilon naught, which is basically the polarization, you know that, and E naught is basically the amplitude. As I mentioned you before that there is no magnetic response, so your only diffractional scattering cross section remains this. This terms goes 0. So only left with this. Now what you have to do is just you have to put the value of electric dipole P. So once you put the value of P, so here you know 4 pi, and there is subside, you know there is square. So 4 pi epsilon naught square, and these terms as it is, which is before in this, and ER minus 1 divided by ER plus 2 whole square, and A3 का square means A6, and there is E star term square, so E star is there, and E incident is there is E naught, and once you take this square, so it becomes E naught square, so you join E naught and E star whole square, and remaining term is basically the E naught, so and there is square, so E naught square. So E naught square cancels with E naught, 4 pi epsilon naught square cancels with 4 pi epsilon naught square, and that's all. So what remain is k power 4 a6 er minus 1 divided by er plus 2 whole square e star e naught whole square. Okay, this is your diffraction scattering cross section. Now what you have to do here to find the parallel and perpendicular, before that you must have to know that the polarization dependence is typically pure electric dipole scattering. Okay, what I mentioned, what I say, the polarization dependence is typically of purely electric dipole scattering, because the scattered radiation is linearly polarized in the plane defined by the dipole moment direction E naught and the unit vector n. So after scattering, so your scattered radiation is linearly polarized. Understood? And typically the incident radiation is unpolarized. So for why we are using this? So to polarize your unpolarized light into linear polarized light. Okay. Incoming is unpolarized. When it's scattered, it becomes linearly polarized, not polarized, but linearly polarized. It is then of interest to ask for the angular distribution. Now it rotates. We just interest is to just angular distribution of the scattered radiation of the defined state of the linear polarization, whereas the polarization vector as I mentioned you in next. Okay, before that, let us find the perpendicular as well as the parallel diffractional case. So in parallel, because it is rotate, so it rotates, so it becomes angle cos of theta. So only this expression becomes cos square theta in this expression. In perpendicular, the angle is zero between the between, you can say that the perpendicular between this E naught 2 equals to E naught. Okay, here your E naught 2 can be equals to this is 2 E2. Okay, this is not naught. So they are in that case, these are perpendicular, so there is no angle, so that's why angle is 0, cos 0 1. So you will only left with this expression. But in parallel case, there is a term of cos square theta because it is rotate. Okay, where this parallel sign and this perpendicular sign indicates the polarization parallel to and perpendicular to the scattering plane respectively. Okay, our next term is to find the polarization, which is the degree of polarization of the scattered radiation. It is defined by this formula, whereas this can be written as d omega perpendicular divided by d sigma perpendicular divided by d omega minus d sigma parallel divided by d omega. Here it is minus and here this is plus. Values is this, just have to put upside is minus, downside is plus. So after taking common cancels with common, you will only left with 1 minus cos square theta and 1 plus cos square theta, and you know that 1 minus cos square theta is basically sin square theta. So this is your dependence of your uh, degree of polarization. Okay, now the diffractional cross section summed our uh, scattered polarization. Our final term is like this: d omega by d and d sigma by d omega equals to k for a6, and this term square, and your this term now becomes equals to 1 by 2, and the factor which is affecting is 1 plus cos square theta. That's why it is 1 plus cos square theta. Now if you want the total scattering cross section, you just have to integrate, you will get this sigma, you can easily find. Okay, so how the graph illustrates that, you can see the graph which is like here you can see is the degree of polarization, here is the diffractional cross section. Your polarization is maximum at theta equals to 90 degree. Okay, because you know that cos 90 is 0, so this is maximum. That's why you can see the peak we got maximum at 0, means at theta equals to 90 degree. Similarly for the case of diffraction cross section, as I mentioned, diffraction cross section directly proportional to 1 by 2 1 plus cos square theta factor. So that's why once you when theta is this is 0, when this is 0 this becomes 1, 1 plus 1 2, 2 cancels with 2, this is you got the lower value, so you can see this peak value we got this depth. So this is how illustrate the graph. Okay, so that's all for today's lecture, in which we discuss about the scattering by a small dielectric sphere, basically the diffractional cross section you can see, and polarization scattered radiation are shown, which I showed you that cos of theta factor. Okay, if you will got the polarization maximum at 90 degree, so at this angle the scattering radiation is 100%. Okay, because you're a peak, so in this angle your scattered radiation is 100% linearly polarized perpendicular to the scattered plane. Okay, it is 100% your at this angle the scattered radiation is 100% and linearly polarized perpendicular to the scattered plane, and for an appreciable range of angle on either side of this and this, you can see this is degrees. The polarization characteristics of the blue sky are an illusion of this phenomena. Okay, your sky turns blue due to this phenomena and are in fact the motivation of led Rayleigh first to consider the problem. Okay, so that's all for this lecture number 23 of advanced electromagnetic field and waves. In our upcoming video, we will discuss another property like scattering by a small perfectly conducting sphere. Till then, take care. Allah Hafiz.